There are several observations that reject current models of the central galaxy parameters. Here we're going to take a look at a few measurements that authors have made that are inconsistent with current models. Because the amplitude and shape of galaxy rotation curves correlate with galaxy luminosity, relationships between galaxy central parameters and large-scale galaxy parameters are unexpected by Newtonian dynamics. The ratio of the rotation velocity in the flat region of the RC and the central velocity dispersion, sigma c, is approximately 1.7 for a sample of SO and spiral galaxies. The maximum circular velocity of giant, round, and nearly non-rotating elliptical galaxies is correlated to the central velocity dispersion. A power law relationship between the circular velocity at the 25th isotope and the central velocity dispersion for a sample that also included elliptical galaxies. The following galaxies were excluded. There's quite a few, as you see, excluded because of warps in the HI disk, non-circular motion of the HI gas in these, and others. These galaxies were included in this study. For high surface brightness galaxies, a linear relation, HSB galaxies with flat ICs were chosen for the sample. Therefore, the scatter in this relation is a function of galaxy mass. The masses of compact stellar clusters at the center of low and intermediate luminosity galaxies also correlate with the mass of host galaxy. The compact stellar clusters and the supermassive black hole modeled as being at the center of high luminosity galaxies should be grouped together under the terminology of central massive objects, CMOs, with mass CMO. The finding of the correlation between the CMO mass and the total mass in a galaxy suggests a similar galaxy formation process. The criteria for excluding galaxies describe characteristics of large influence of neighbor galaxies. See the video STOE asymmetric rotation curves. Keplerian motion to within 1 part in 100 in elliptical orbits of stars that are from less than a parsec to a few thousand parsec from the center of galaxies have been observed. The stars within 9 light hours of the galaxy center, you will note that the capital G signifies the Milky Way galaxy. These stars have velocities of 1,300 kilometers per second to 9,000 kilometers per second with high accelerations. Newtonian dynamics suggest a huge amount of mass, such as millions of black holes, dense stars, and ionized iron, must be inside the innermost orbit of luminous matter. The central mass varies among galaxies from 10 to the 6th sun masses to 10 to the 10th sun masses. The ratio of the central mass to the mass of dark matter halo, thought to be around spiral galaxies, is a positive value that decreased with the dark matter mass. The central mass can be distributed or central volume with a density of at least 10 to the 12 sun masses per cubic parsec. That the central mass is crowded into a sphere with a radius of less than 45 AU is proven. That the structure of the central mass is a supermassive black hole is widely accepted, but unproven. The Newtonian model implies the central mass must either quickly dissipate or must quickly collapse into a supermassive black hole. The long-term maintenance of the central mass rules out the first possibility. There may be some extended mass around Sagittarius A. Observations have ruled out many models of the nature of the central mass of galaxies. Observations inconsistent with the supermassive black hole model include shells of outflowing shocked gas around the galactic nuclei suggest a repulsive force called the wind by some authors, exerts a repulsive force acting on the cross-section area of particles. You will note that these outflowing gas also reject the idea in the Big Bang where matter is inflowing into spiral galaxies. Therefore, denser particles such as black holes move inward relative to less dense particles. Less dense particles such as hydrogen gas move outward with the wind. The central supermassive black hole is apparently inactive for its size. There are a multitude of X-ray point sources, highly ionized iron, and radio flares without accompanying large variation at longer wavelengths reported near the center of the Milky Way. Models require the presence of longer wavelengths if you have these X-ray point sources. The challenge is to form a model of a galaxy that explains all these different observations. A total of 82 host sample galaxies were used for the calculation. Of the host galaxies, 60 are source galaxies and 22 are sync galaxies. Source galaxies are spiral galaxies, sync galaxies are elliptical galaxies. The galaxies mentioned as omitted from the other studies were included in this sample. 29 galaxies had both a central mass and a central velocity dispersion calculated for them. And here's how they plot the central mass versus the luminosity. You will notice how similar this is to the rotation curve kind of model. Applying the same method used for rotation curves, that the Newtonian spherical property applies, and that the source was internal to orbits of the mass within 45 AU of the center, we end up with equations very similar to the rotation curve. The result, of course, has very good agreement. The suggested central mass structure is a central source of a matter-repulsive plenum density proportional to the inverse radius, where the radius is galactocentric radius, surrounded by a spherical shell of matter. The STOE suggests the luminosity proportional to the source strength, and therefore the force on the surface cross-section of the matter, which is F sub s, is proportional to the gradient of the plenum. Therefore, the galaxies with larger luminosity will have more mass in the center shell to balance the higher surface force strength with the gravitational force Fg. Therefore, the STOE naturally leads to the smoothness of the central mass with the galactic mass relation for the full range of CMO spiral galaxies. If this speculation is essentially correct, then the correlation of central parameters with spiral galaxy global and RC parameters suggests not only a similar galaxy formation process, but also a self-regulatory negative feedback process continually occurring. Feedback processes have been suggested in several recent studies of galaxies with central massive objects. The source strength is the control of the negative feedback process. If the mass of the central massive object increases, the gravitational force increases and mass migrates inward. At very high rho, which is close to the center of the galaxy, the high repulsive surface force compresses matter. The mass, say such as a black hole, cracks like a complex molecule in the high heat and pressure of a fractal distillation process, and matter is reclaimed as radiation and elementary particles that form hydrogen. Note, the video required the distance between Hodge to be inversely proportional to the surrounding plenum density, which is consistent then with this model. This accounts for the large amount of hydrogen outflowing from the galaxy center and the shocked gas near the galaxy center. A single black hole reclamation event is consistent with the periodic X-ray pulses from the galaxy center that also do not have the other frequencies emitted with them. Further, the feedback loop controlled by the source strength is the connection among the central parameters, outer RC parameters, and the global parameters of spiral galaxies. The special focus of the present investigation included galaxies that are problematic in other models. The sample included galaxies with rising, flat, and declining rotation curves, galaxies with a wide range of characteristics, and galaxies excluded from samples of other studies. Considering the range of observation and the range of galaxy characteristics with which the STOE is consistent, the STOE is a relatively simple model. This is the STOE galaxy cluster model. Here we have the source, and coming out from the source is hydrogen, light, and Hodge, which are ejected. Hydrogen goes out to near the end of the galaxy. Some of it forms suns, which then travel inward and eventually form a nova. One output of the nova are neutron stars, which turn eventually into black holes, which then end up back in the center, and then the plenum density of the center cracks the black holes into hydrogen light again. Some of the output of the nova are heavier elements. Some go back into suns. Some of these elements end up going between galaxies and into a sync galaxy. Of course, they come in rather hot, and so they're ejected again, go out a little ways, and then come back in what's called a cooling flow. This paper lists all the references for the various observations we made.